Okay, so thanks for the introduction. So yesterday I gave some kind of overview about, well, for example, why we care or what kind of things we're heading towards. On the other hand, I haven't even finished the examples. I just started with the very first example. So we're going to have some more examples today, and when we are all tired of that, we'll move on to some other things. Like, for example, why are Shimura varieties even varieties? I mean, they're not clear, right? So far, they're just quotients of something. Okay, so yesterday we have the following. So we introduced the case that we have the symplectic group, for example, and it acts on some kind of generalization of the upper half plane, which is the Ziegler upper half space. And these are the symmetry matrices. I would just write this over the complex numbers such that the imaginary part is greater than 0. And one remark I want to make is that just like in the case of SCO2, you can also consider GO2 action if you include both the upper and lower half planes. Here you can also imagine that there's also something like a lower half space in the generality. So there's something people define to be GSP. I'm going to write down the definition of this for all rings. And this acts on the kind of things plus minus. And this time we have similar thing, but then we have, well, instead of saying that we have, you shouldn't just drop this condition, right? You actually have either positive definite or negative definite, and there are many things in between or outside. So such that they're definite, so either it's plus or minus, but it doesn't mean they're just on 0. There are the two extreme cases. And let me tell you what this GSP really is. For any ring, so you now consider all the, so this is something like this. So I add an additional element there, which is just going to be a scalar. Well, let me just write 2n r. But then I have the invertible elements, and now the difference will be that previously we have this equal to exactly the same thing, but now you're allowed to adjust your pairing up to a scalar. So this is something preserving the pairing up to some number, and this R is usually called the similitude. So it's not really preserving the pairing exactly, but they are allowed to be up to a scalar. And if you allow something like this, then your group is larger, and you also act on a slightly larger space, in fact, not too much larger. And you might wonder what is the advantage of this. One advantage will be the following. So if you remember, we had something like this H naught from U1R to the real points of this group. I just sent A plus BI. What was the sign convention yesterday? So I think it was something like this. Well, each of them are actually n by n blocks, to be fair. And now you can actually do the same, but with a larger thing here. So this can be changed to all the invertible complex numbers. Now I include this. Well, same expression, but now, of course, you have also the scalars. So, for example, you can scale everything by a common non-zero real number. And the advantage is that this second thing is actually better for the purpose of studying the so-called variation of Hauss structures. Not enough space to be here. I write this, and let me write on the other board. I guess the only difference is that now we have this scalar telling you the weight of the Hauss structure. And this is useful in Delisle's point of view of thinking of all Shimura varieties as some kind of parameter space for variation of Hauss structures. Anyway, this is something useful to keep in mind, although I won't really go into details now. But just keep this keyword in mind. This variation of Hauss structure is useful when you go on to study the more abstract theory of this thing. And later, in all the examples I talk about, I will give you something which is like the symplectic group over there, and you can imagine there's actually some kind of larger group, which is larger just in a very simple way. And in those cases, you can actually more easily study things like this rather than that. And in fact, in the so-called definition of Shimura datum, you actually have this second kind of thing. And this is important that you have this weight encoded there. Okay, so let me come back to the examples I wanted to talk about. So the next one I'm going to talk about is the unitary groups. Did I number the example last time? I don't know. Okay, second example, and now I will start with the unitary groups. So I will first start with the easier way to define unitary groups and give you some domain, and then I will actually modify it to make it easier for some other purposes. So I still have this IPQ being this simple-minded matrix with ones on the top P entries and the negative ones on the bottom Q entries. And these P and Q are going to be a so-called signature, and we can define, for example, the unitary group. Well, I just write R here just to remind you that we're actually thinking of it as a group over R, although the entries are actually over C. And now we have instead of putting the real numbers here, as in the case of orthogonal groups, now I'm putting the complex numbers here. And what I want to preserve is actually a Hermitian pairing instead of a biennial pairing. So I have complex conjugation on the top of it. Okay, so I have something like this. And now this is a group, and also you can actually try to write down the domain. So I guess there are choices. Let me consider first. So I'm not writing the same notation like HN or something. I'm using now slightly different kind of system of notation. I write D here. And the reason will be clear in fact, I will also give another realization. And this first realization is more like a generalization of a disk. So that's why I put D there. And this is all the matrices. And this time, I have a complex conjugation on the top. And this is, if you spell it out, this is something like this. Okay. So for example, if P and Q are both 1, this one is just the unit disk on the plane. So this is a situation where you sort of do a change of coordinate in some sense. So as a group, this U11 is actually very similar to this SL2. I mean, it's just up to some minor difference. But as a domain, when we write things differently, now you see a different realization. And this is actually one realization of this kind of group and this kind of domain. Now I'm going to give you another realization. By the way, before I move on, let me just emphasize that for the same reason, if I write an expression like this, it's clear that it is preserved by the group action just because, again, this expression is just preserved by the conjugation action on both sides. And I have this complex conjugation corresponding to that complex conjugation there. Now so this is something I would call a bounded realization. And maybe it's only for psychological reason that sometimes it's also helpful to have another realization where you can talk about infinity. There, everything is actually finite. But let me also consider another realization. And this realization also suggests some relation between this group, abstractly, and the symplectic group I've talked about. And in fact, this will be important because in the end, we actually want to think of this as something which is actually inside the symplectic group. And this will be something useful. So the other realization I'm going to talk about is, well, I'm abusing notation. I'm denoting it the same way, but it's now a different definition. In the end, it's all about preserving a slightly different pairing. But instead of using the Hermitian pairing here, I'm going to use skew Hermitian pairing instead of Hermitian 1. And in fact, I have to make some choices. So I will write this JPQ to be something like, well, now we're upgrading from 2 by 2 matrices up to 3 by 3. So I'll write this way. And then it's S in the middle. S. I will write this to be this. So what does this mean? This actually means this thing is Hermitian and positively definite. So the original S is actually skew Hermitian. And if I actually take the trace, well, just from the complex number to a real number of this skew Hermitian pairing, I actually get the alternating pairing. And that is how I can, for example, attach to each element here its image in the symplectic group. So in fact, there's a natural way to map elements here to some larger symplectic group. So basically, if you have a skew Hermitian pairing, you just take the trace of the value, then you get an alternating pairing in that case. Sorry? Oh, I mean, there's a size of this thing. So size P plus Q. So this is size P minus Q. So I guess to make sense of this, I have to make sure P is greater than or equal to Q, right? So yeah, assume this. So this is size P minus Q. And in case P equal to Q, this S is just not there. There's just no entry there. Well, you probably can guess what I'm going to write here. So this time you preserve this pairing. And you can also consider a simulated version of this. So instead of having just one element here, you add another scalar, and you preserve the pairing up to the scalar, then you have the simulated version, which you can call the GU instead of just U. And this one also acts on a domain. So this time, well, this is the second definition. It acts on, this is slight abuse of notation, so I'm still using H, but I put a PQ there. This is now, well, you need more entries here, and I will put it this way. I will put it like a, more wordy now. So the full size is still P and Q, but this one is a Q by Q block, and this one is P minus Q and Q. And this is not the end of the line, so we still have this, well, times this JPQ times ZW1, but then I will put a conjugation here and put a transpose here, and this one I want it to be multiplied by minus I, and this one, if you spell it out, becomes something like this. And this is required to be negative definite. Okay, so this is the sort of more complicated domain. Well, while this looks more complicated, this actually ends up being slightly easier for calculations for various reasons. One of the explanations will be the following. So for this kind of matrix, it's easier to talk about the so-called, well, so if you think about the case of SL2 or GL2, there's this convenient upper triangular matrices. Those upper triangular matrices preserve this infinity, I mean on the boundary, this cusp. In this boundary realization, those things are not infinity, right? Those actually are some points on the disk. So they have their coordinates. But if you use a projected coordinate, infinity has a very simple coordinate. It's just something like 1 above 0 or something like that. And this kind of realization allows you to more easily write down those kind of simple-minded elements, while this one will require more careful treatment. So if you try to write down the so-called parabolic subgroups, which are generalization of these upper triangular matrices, those, well, in both cases, of course, the groups are the same. Right? They are isomorphic to each other, so of course you can do the same. But the expression for a parabolic subgroup will be much easier in the bottom case than in the upper case. Another explanation for this to be easier is that in the case of many groups, these parabolic subgroups are actually stabilizers, some kind of filtrations. And it's easy to see that there are some very nice filtration here because you have 0 all the way here. So for example, if you consider all the elements with only the first Q entries being non-zero, those are stabilized by this kind of group elements, just because of the way you define them. So there are many practical reasons, but maybe not theoretical reasons for this to be easier to work with. So anyway, I will come back to these parabolic subgroups later when I actually talk about the so-called boundary components, namely the generalization of the cusps. Just keep in mind that there is some reason we do this way. Well, there are still several things you can, well, these are maybe all exercises. So firstly, these are really the same group. These are really isomorphic domains. You can find it easy to find some kind of change of coordinates. You see this choice of S there, and you might wonder why I don't just write down some easy choice like I there. That's because in practice, when we talk about unitary groups, we actually like to talk about their rational structures. And their rational structures might be over the Gaussian numbers, for example. You might want to have like some square root of D for some choice of D. So I want to keep that choice possible here. So this one can actually be taken to be rational over your favorite imaginary quadratic field. Or more generally, you can take products of this and talk about CM field and so on. So that's why I leave this as a choice here. So this one might be chosen according to your need. So if you have other kind of rational structure, you choose differently. And this is slightly different because in the symplectic group case, you have less choices to start with. But in the case of unitary groups, naturally we are working with some kind of quadratic extension somewhere. And those choices are important when you talk about the applications, I mean arithmetic applications. Okay, so I'm not sure how much more I should say about this example, but let me also remind you that it's actually possible to define these things in some other. If you remember yesterday when I talked about the symplectic groups, I actually tried to write down a kind of general way of defining them, allowing me to change the choices of these kind of pairings. So let me also remind you that you can do something like this here, but you have to have some kind of different point of view. So let me just take a special case, P equal to Q, and see how things become. So in this case, we have the domain is actually not so hard to describe. This is actually just, well, we don't have the W in this case because P equal to Q, so we don't have this W. So it's essentially just one matrix. And the condition is also not too hard to describe. So here I wrote the condition to be over there. It is, well, did I write down anything? It's over here, yes. But this is actually the same as saying that there's some kind of imaginary part. So let me write down it, and then, so I would talk about imaginary part of Z greater than 0. But what does this imaginary part mean? So this P, this Q, QC, well, this is actually something you can reinterpret as taking all the Hermitian matrices over the complex numbers, and I just formally tensor up to complex number. Well, this might sound like a headache. So what does that really mean? So you can write every matrix as a sum of a Hermitian matrix, a skew Hermitian matrix. I force myself to think about the skew Hermitian matrix as a I times some Hermitian matrix. So when I write this imaginary part, this is really an imaginary part, meaning the skew Hermitian part of the matrix. So this is more like the skew Hermitian part. Yeah, so again, let me repeat. So for every matrix here, you can really just write it as a sum of canonically as a sum of Hermitian and skew Hermitian matrix. You can actually treat the skew Hermitian matrix as like I times a Hermitian matrix. Yeah, so this is a way to think about this. And then this looks actually like the same thing you see in the Ziegel case. Because in the Ziegel case, you have the real matrices which are symmetric, and then you consider the compactification of that and take the elements which have imaginary part being positive definite. Now I'm doing the same, but I upgrade from symmetry matrices up to Hermitian matrices. And then after I have Hermitian matrices, I tensor up to C, And then it looks like the usual Q by Q matrices, but in fact, this is actually secretly a compactification of the Hermitian matrices. And then in this case, I think about its imaginary part and require it to be positive definite, and that's the domain. So in fact, this is the same theory, but when we write the coordinates, our priori looks very different. So I don't know how you feel about it, but when I first see those papers about unitary groups, they just have magical choices about these things. But on the other hand, behind the scene, they are actually based on the same principles. Another thing I would just mention in words is that you can also try to define these domains by requiring the condition that this is a remark. It's also possible to think about some kind of condition. So you have a pairing. Let me just write it as Q. Then you can think about this as like Q V equal to 0 and Q V bar V. Well, I used to my times minus I negative definite. This is the same thing I use when I talk about the Ziegel case. I write down this symplectic pairing. You can actually try to do the same thing in Q, but now it has to be on complexified vector space. So this is kind of confusing now because we already start with a complex vector space, but you have to forget about its complex structure and think of it as a real vector space, and then further complexify it. And then you can write down these coordinates, and if you do some kind of change of coordinate, it will become exactly the same thing there. So I'm going to skip this detail, but this is just reconfirming that we have this basically the same principle behind all these coordinate choices. Well, this is only the first new example. Now the complexity level will still go up. I guess we have sort of smaller and smaller groups, starting with the symplectic group. And then you have more and more defining iterations, and then the complexity level goes up. But again, I'll emphasize that they are still the same theory behind them. And one thing I would just mention in words is that yesterday we have this sort of moduli interpretation of the Ziegel case. So the points on the quotient of the upper half plane, the Ziegel upper half space, had the meaning of parameterized and polarized Abelian varieties. Today we have a more complicated pairing. This is a Hermitian pairing, so it has a more structure given by this complex structure on it. It actually corresponds to Abelian varieties with additional endomorphisms. And this is something which can be further generalized. So here we're only talking about the real point here. And in fact, it's possible to classify all the endomorphisms of Abelian varieties. And in fact, this is sort of the first non-trivial case of the so-called PL type Shimura variety. I'm going to come back to this later, but this P is the polarization I already mentioned. The L is the level structures I already mentioned. This E is just the endomorphism, this extra structure on the vector space we talk about. So here you see this complex structure. In fact, when you define the rational structure, you will require some kind of like imaginary quadratic field. So those things will show up. Well, the next example is another example which is still sort of the standard thing you can see in the PL type theory, but the group gets much more complicated now. So I will not really say too much about it, but I'll just write down it to let you know this case exists. Well, there's a star there. The reason is that this is not the usual orthogonal group you see. There's some kind of funny way to define this thing. So I would just write this way. So this is a subgroup of SO2N-C preserving the skew Hermitian pairing defined by, well, one special case there, something like this. So this is like the intersection of this SO2N-C with some kind of unitary group of signature NN, but defined in the second way over there. And this might be a good example to emphasize that given the same group over the complex number, you actually might have more than one possible real form of the group. So the reason there's a star there is that this is actually different from the usual SO2NR, which is a compact group. This one is not. This one is some other way to realize a real group. And I think this is part of the history that you have all these kind of special notations. But in any case, this is another group, and now the question is whether this group has an attached kind of Hermitian symmetry space to act on. And the answer is, of course, yes. Otherwise, I won't be mentioning it. So this acts on, well, I'm running out of notations. I will just write this SO2 and star. And I'm just writing this n here. It means n by matrices. Now, again, I have two equations. The first one is sort of the orthogonal group relation. And the second one is the inequality well, this is the imaginary part kind of thing. Okay, so, well, sorry for messing up the board. There's, yeah. Well, this is a bit different from the previous one because now in practice, we actually have two defining equations here. So something hiding behind this is that, in fact, there are another two relations, and when you use this interpretation, you actually have another two relations, but they got kind of hidden when you summarize the thing there. This one is even more complicated than the unitary case, but there is actually a special case. So when n is actually even, there is actually a way to define this thing using, again, something similar to this. So when it's equal to even, well, this time this is 4k. It can be realized as the following thing. So as a subgroup, well, this is probably an abuse of notation. This thing doesn't really make sense, but let me write it this way. Because previously I only defined this SP notation for commutative rings, but now I'm writing down the Hamiltonians there. This is not commutative. Well, but still, you can imagine its definition. So it's all those Hamiltonian matrices preserving the pairing. So, so it's a subgroup of, well, 2k by 2k matrices over Hamiltonians preserving the skew Hermitian pairing. Well, you can talk about Hermitian pairings over any kinds of these kind of algebras have with some kind of evolution there. So you can talk about complex conjugation on this H, which is not exactly the complex conjugation, but this Hamiltonian kind of involution, sending like I to minus I, J to minus J, and so on. So the skew Hermitian pairing defined by 0, 1, minus 1, 0 with n entries there. Sorry, k entries there. And you shouldn't be surprised that in this case, the domain, again, has an expression in terms of imaginary parts of some compactification. Well, this is actually isomorphic to all the elements. Well, this is, again, some kind of abuse of notation. All the Hamiltonian matrices which are Hermitian with imaginary part positive definite. Well, we are using now all three kinds of associative normed algebra over R. So we have R for the symplectic case. We have C for the case of the signature NN unitary groups. And now we have another case which uses Hamiltonians. In fact, later we will see another example using the octonians. And And that will be the end of it. There's no other normal algebra we can use. That one is not even associative, so I don't want to pretend I can really work with them, but we can know its existence. Okay, so this is yet another example, and this example is actually also one that will show up in the so-called PO type setup. But then you have to consider those abelian varieties with additional endomorphisms given by things related to the Hamiltonians. It's not just a quadratic extension, but it's actually a non-commutative kind of thing, which is quaternion over your favorite field. I didn't really say it, but all these things can be upgraded in some sense to allow, for example, several copies of things product together. In that case, you can have the rational structure given by some group over like the total real field instead of just Q. So I didn't say it, but those are possible. So here I'm mainly only writing down the real structure, but in fact, in practice, you don't just have this kind of thing. These are like the very simple components of the things over R, but we're not really working over R. We're actually working over something over Q. And over Q, you really have something which is not really absolutely simple. So if you go to R or go to C, of course, it breaks up. But over the rational numbers, you might have to require several copies to be put together. Well, this is the third example. So the first three examples are basically things you will see in the so-called PO type setup. I haven't really told you what those things really are, but let me just mention the keyword now. But starting with this example, we're going to see things which are not going to be really PO type things. So in some sense, they are more strange. I mean, they're not as simple-minded as this. So for example, the relation will not be so clear between these kind of things and the next kind of things, which are also going to group. But on the other hand, this is actually a reasonably simple-minded group. So let me just remind you that these are all the elements preserving this bilinear pairing defined by this matrix 1p minus 1q. And this is not going to be a simple-minded example in the sense that when you try to think about its modular interpretation, this one is going to be much more complicated than the previous ones, although the expression here might actually be simpler to begin in the beginning. So this one will lead to examples which are so-called abelian type, or if you talk about the so-called spin group above, then it will be something we call Hash type. But in any case, these are not as simple as the first three examples when you try to think about their actual meaning. On the other hand, the domain is not so bad. So let me start with this. Oh, wow. I'm really running out of notation, so I'll just write groups as subscripts here. So I will just write this way. So this V is actually the space there. And the way you think about it is that this is some kind of representation space for this group. So this group, of course, acts on V. And then I think about its compactification. And then I think about, well, the familiar kind of expression. I just preserve this pairing and compactify this element here, require this thing to be, well, like this. It's not exactly the same expression, but quite similar. But this time I will, again, consider the projective coordinates, not just exactly the same coordinate. So it's a projective coordinate as usual. I didn't really say anything about the actions, but they're all the same. So when I write that expression ZW1, those are the familiar projective coordinates. So after I multiply, I divide out the last entry. Here, I don't really divide out S entry. I just take the whole thing and identify elements up to a scalar. So this is really working over, so this is work over P1V. Let me see. But this is convenient to start with. But on the other hand, to see the relation between this thing with the previous examples, there's another way to write the same coordinate. And I think this is fun by itself, so I will talk about it, although you might think this is starting to be like some kind of more like art than science. Okay, so this time I will do the following. I will decompose V to be two spaces. So V, a priori, is this P plus Q. I will decompose it into some P-dimensional space and a two-dimensional space. And this one has pairing. This one has pairing 1P minus 1Q. I want the pairing here to be 1P minus 1 minus 1. This just means one entry here. This one, well, this might seem artificial at this moment, but just to save the notation for later, I write this way. So this is actually signature 1, 1. But it's like a conjugated thing, so it looks like the same sign. So this is not minus 1. These are both positive. And I only put a 2 to simplify some equations later. It might seem unfair at this moment. Then, so denote the coordinates. The first P will be denoted Z, and now I have W1, W2. Well, I hope you can see here. There's a W1, W2 there. And then this domain is isomorphic to, well, it's just by definition being something like this. Well, this is only the first equation, and I have a second equation over there. This is the one about the sizes. So when you put the complex conjugation, they multiply together and give you this absolute value. Yes? I haven't said anything, but I would say it. At this moment, I haven't really talked about any further structure. Which one? Ah, you mean this second page? Yes. For this second page, yes. Yes. Even the top page, yes. Yeah. Q equal to 2 from now. Thank you. Yeah, for the thing there, maybe it doesn't matter, but starting from this page, I'm using Q equal to 2. Yeah. Yeah, so to be fair, I didn't really say what this is, right? So in fact, this one is not Hermitian unless Q equal to 2. And in some sense, I'm trying to explain that over here. Yeah, sorry about that confusion. This one is now negative. Okay. Well, why is this useful? So if W2 were 0, indicating that it's not going to happen, then what do we get? Then we get this following funny equation. This Z1 square sum to Z P minus 1 square. Well, because everything here about W is 0, because if you multiply 0 with W1, whatever it is just 0 there. This becomes smaller than, well, ZP square. But ZP square, you know, is equal to those sums. Well, sum all together. Well, is this possible? This is not really a question about Shimura varieties, right? Something really basic is wrong, so not possible. Well, can be true. Cannot be true. So it means that W2 is not going to be 0. If it's not going to be 0, then it's some scalar, but we are working with the projected coordinates. So you can pretty much just divide it out. So you can divide out W2. And once you divide out W2, you can assume it is just 1. And if you set W2 to be 1, then W1 is going to be determined by everything else. So that means you don't really need all these coordinates. You can drop W1 and W2 by assuming W2 is 1. So may assume this is by dividing non-zero values. You can assume it is 1, but once you assume it is 1, then W1 is determined by all this, everything else. And you can plug in this into the second equation. Then the condition becomes, well, in the end, you see that this is actually, well, Q is actually equal to 2 now. This is isomorphic to the following domain, which is you can consider all the P entries with coordinates Z1 up to Zp. And the condition is actually simple-minded. Well, I'm not going to explain all the details, but this is now, I will put it this way. In the sense that if yi is imaginary part of zi, and y is all these things together, then you have a simple-minded equation being just this yp squared greater than y1 squared, yp minus 1 squared. I try to write this as another imaginary part relation just to indicate that this is similar to all the previous examples. You start with some kind of space, you define some kind of notion of imaginary part being positive definite, and then you write it down. And these are actually not just artificial. In fact, there is something we call Jordan algebras, and all these examples of Hermitian matrices over R or C or Hamiltonians, or even this funny thing, is actually examples of Jordan algebras. And this particular thing there is just this light cone kind of thing. And this is actually not connected. It's actually two connected components. Yeah, so it's a bit different from the previous examples. And now you actually have some plus component, and this is minus component. This is vertical yp coordinate. And there's actually a subgroup. I'm afraid I'm going to force you to use Google here. The subgroup of SO, PQ, R of elements with spinor norm. I actually checked. This one is easy to find on Google. So spinor norm plus 1 preserves the plus component. Yeah. Anyway, now I mentioned this keyword spinors, and in fact, oh, I don't really want to erase this first line here in this example. I will erase the bottom part there. Sorry, the top part there. This SO PQ R has a cover by, well, twofold cover by something called spin group. And the interesting thing is that the action, once you have a twofold cover, so this means that as the spin group also acts on this SOPQ as well. So if you remember, last time I mentioned that when we study Shimura varieties, I probably have to choose a group and a domain to act on. Here we sort of have some choice. We can either have this spin group or this SO acting on it. And they're actually not the same when you think about arithmetic applications. But if you think about domains, they're the same. So when you look at the kinetic components, they're the same thing. But when you actually look at the relational structure of the groups, they're not the same. And in fact, this is the subtle distinction between the so-called Hodge type and abelian type things. So the difference is the following. The difference is that, I guess I really have to erase something. I will erase this bottom part. This SOPQ doesn't really have a map to the so-called symplectic group. But all the other examples we have so far has a map to there. But the spin group actually has a map to some symplectic group. This spin PQ has a map, well, can be embedded in. I'm not going to give you the precise number, but in a very large, usually very large, 2 to some power symplectic group. And this SO is not. Cannot, well. So this is a subtle difference. So this case using the spin group is something people will call the Hodge type case. The reason is because it is not just embedding a symplectic group. You can actually use some kind of linear algebra to cut down this group. And those are the so-called Hodge tensors. So you can start with abelian varieties and talk about not just the polarization and homomorphism and level structures, but use even more structures. So it's like a abelian variety. This parameterizing abelian varieties with so-called Hodge tensors. The price you pay is that you have to really look at very large abelian varieties. So for example, you might have heard of the so-called mode drive K3 surfaces. Then you have to go to 2 to something like 20 or 19 power, I mean some large power of dimension of the space. On the other hand, this SO itself is not. So it's only the connected components which are the same as those one. And also, in Shou's lecture, he mentioned the so-called Shimura curve. They are related to quaternion algebras. Quaternion algebras have their structures which are actually given by some kind of orthogonal group. They are not really the spin group. So those Shimura curves are actually examples of this kind, but not that kind. And these kind of things are called abelian type. It's the same connected components as the Hodge type, but when you look at the rational structure, they are not the same. So when you try to descend things down to some number field, they become different. But when you just look at the domains and all these things over large fields, they look like the same. So they have the same kind of connected components, but their arithmetic meanings are very different. Yeah, so all the previous 3 examples are mainly things we will care about in the so-called PEL type. And starting from this example, you see things which are not really parameterizing abelian varieties with this easy, simple-minded PEL structures. You really need something more complicated in general, and these are the Hodge type and also abelian type kind of things. Yeah, only for Q equal to 2. So what I showed here, what I didn't really emphasize, but what I showed here is that when Q equal to 2, you can actually write down a very simple-minded kind of domain, and that's actually a Hermitian domain. But when Q is not equal to 2, this is not true. Well, obviously, we use the fact that we only have W1 and W2 there. And also this one actually, for example, if P equal to 1, that is simple, right? When P equal to 1, this is just the upper half plane. Yeah, so this is another kind of generalization of upper half plane, but in a very different kind of way. Yeah, instead of looking at Hermitian matrices and so on, you look at just more numbers. Yeah, so. Yeah, so all these types of different types of things become the same when they are very small. These are the so-called exceptional kind of isomorphisms. A lot of interesting applications of these kind of things to number theory so far have been built on lots of very nice and convenient exceptional isomorphisms. But unfortunately, they will be really different when numbers are large. Well, so far I have never mentioned all these types, right? So like A, B, C, D, E, whatever they are. So, okay, I was just saying words. So when people call it types, they're actually talking about the classification of the groups. So if you know it, the groups, the algebraic groups can be classified using the so-called root systems for them, and they are Dynkin diagrams. So the types of the corresponding Dynkin diagrams give you the types of all these things. So maybe I should just write down some table. So this is just for convenience, because sometimes you don't want to repeat all the names. You just say, well, this is what type of Shimura variety. So these symplectic groups are something we call type C. And for unitary groups, well, to be fair, the classification of real groups are much more complicated, but if you go to the algebraic closure over C, they are isomorphic to just GLN with n equal to P plus Q. So this is so-called type A. But the A actually is for this general linear group. But in any case, in the classification of real groups, you have much more refined. So you have several different kinds of type A things, and you can still find that number. For SO, it really depends on which kind of SO you're talking about. So I mentioned this SO2n star. This is type D. But I think, for example, in Deling's article, he will write type D H, probably to indicate some closer relation to Hamiltonians. I'm not sure if that's the reason, but in any case, we still have just new example here, P2, Q is being 2. This one depends on parity. So, or D, this is when P odd and P even. So the parity actually matters when you try to determine the type of orthogonal groups. And this is type DR. Okay. I don't know exactly why it's called DR, but anyway, it's probably, it is not using anything Hamiltonian. I have to be more careful. So when I mention these classifications, I only mention one factor here. And as I said, when you work with rational structures, sometimes you can have a group over Q, which is not really simple when you go up to R. So you can break up when you tensor up to, base change to R. And if you have a mixture of both type DR and DH, then we don't really know how to relate them to this kind of things like abelian varieties and so on. So already in the type D world, you have exceptional type things. They are not exceptional groups, but they are not really Hauss type or abelian type. So it's just a remark. If you have mixture of types DR and DH in the same Q simple factor of the group, this means over Q they look like the same factor, but over R they don't look like the same factor. Not abelian type. Yeah, so what I said there is only fair when you have the same kind of things together. So if they're all type DR or all type DH, you can still talk about these things, but not when you have a mixture. But this doesn't finish all the possible list of simple-minded examples. There are just two more simple cases. Well, I should say are simple cases. Even over R, there are simple cases. This is E6 and E7. Well, as I said, this is only according to the classification using Dinkin diagrams. And I think for most people, these two groups don't have any meaning beyond just the diagrams. I'm not even going to draw the diagrams, but I mentioned octonians, so maybe I can at least mention why they are useful. So I think some people say that we have exceptional groups only because we have octonians, but to be honest, I still don't know how to give a very easy explanation of very easy description of the domain for E6. But for E7, it's not so bad. I apologize, I'm not going to review the definition of E7. I actually prepared it, but I think I don't have time to do it. So firstly, there are actually more than one E7 you can talk about. So yeah, so which E7 are we talking about? So for those of you who are curious, well, to use any kind of Google or whatever references, let me mention that it is actually Cardano index, this number, and it actually acts on a domain. I would just write HE7, and there are those Hermitian 3x3 matrices over octonians. So we are happy with this octonians and Hermitian matrices compressified. Well, this is like a nightmare, right? You already have octonian and then you further compressify it. The equation is simple-minded. It's just imaginary part positive definite. Yeah, you can even diagonalize over the octonions, despite the fact that this is not associated algebra. So anyway, it's a normed algebra, and it's actually something you can diagonalize. Well, but I'm not sure how much more I can say about it, but well, you can just count the dimension, right? So if you have a 3x3 matrix, Hermitian means all the diagonal entries are real. Well, I mean, not real, in this case, complex number. All the off-diagonal entries, below the diagonal, the entries will be determined by the entries above the diagonal. So in total, you have 8 times 3 plus 3. So 27 dimensional over C. I would just mention the other case without giving any detail. The other case is E6, the Cardan index is minus 16, x on something, dimension over C equal to 16. It's possible to describe the domain using only 2 octonian numbers, but I haven't found a very nice way to give the relations. And in fact, if I really want to define the E7, I would have to introduce another 2 kinds of E6. So in the same page, you see potentially 3 different kinds of E6. They are all different as a real group. Anyway, I'm not going to say too much more, but I have to say that as far as I know, we don't have any nice modular interpretation of these things. So you can describe them as variation of House structures, in some sense, the domain for them. But if you want to think about them as like moduli space for varieties with additional structures, we just don't know. So although there are only 2 of them, but we still have not, we still don't feel we understand what they are. And also, although this group is smaller than that one, the description is more complicated. It's probably similar to the case that the unitary groups and these other orthogonal groups are supposedly smaller groups, but in fact they are embedding a much larger symplectic groups. So it's similar, right? Here, you have a larger group, but in some sense the domain is simpler. And this is a smaller group, but in fact you need more irrigations to cut down the thing from here down to something like this. Yeah, so I haven't found a nice way to do it, but anyway, these are just for intellectual curiosity, I guess. If you really know how to work with those things, I guess people will still be very happy. So, for example, we don't really know how to define nice integral models of these things. We don't know. Wow. 5 minutes left. So, what can we do next? So, in the title, we have not just Shimura varieties, and we also have the compactifications. So, I will just give you a preview of what we're going to talk about next. So we have nice compactifications. Of quotients like let me start with here and just call it X gamma. So this is only at the level of quotients of symmetry domains. And there are actually very many different ways to compactify them. They are useful for different purposes. And I believe that in the afternoon you will probably hear one kind of compactification, which I'm not really going to talk about next time. So this is actually true for not just the Hermitian symmetry domains. You can actually work with all kinds of Riemannian symmetry domains. There is something that people call the Barrère-Serre compactification. These are, in some sense, very nice compactifications for the purpose of studying cohomology, but not for the purpose of other kind of arithmetic operations like finding congruence and other things. The reason is because these are manifolds with something they call corners. Well, how do I explain that? So in the case of upper half plane, for example, you have the cusps in the algebraic geometric language. But Barrère-Serre compactification, they don't really talk about cusps. They actually have circles instead of just points. Well, you can still call them cusps, but they don't hurt you. Okay, so if you think about the upper half plane case, a priori you have something like this. And now if you think about this is kind of abuse of language, near the infinity, this quotient looks like the puncture disk. There is a point missing there. So in all the other compactifications we have, like this just Riemann surface compactification, we basically just remove that point, just fill the puncture there. But then you lose the cohomology class. So, well, in fact, obviously there's a circle there. So if you try to shrink the circle, and if you don't have that point, then the circle will be gone. It becomes constructible. So lose cohomology class. If we just fill the puncture, then we lose the cohomology class. So an easy solution will be just to keep a circle there. And if you keep a circle there, you do get a compactified space. It's never going to be a variety because the varieties just don't have that kind of refined topological structure to allow you to do that. So the Borel-Serre compactification, you consider circles instead of this actual mixing point. Well, so this is something I think we'll be talking about in the afternoon in Bridget Spett's lecture. So the point is that although this looks kind of weird, this is nice for topological applications because it actually preserves all the cohomology classes, and it becomes easy to work with compared with other kind of compactifications. So useful for cohomology. But maybe not so useful for other applications like studying Gauss orientations or studying congruences and so on. So there are actually some more algebraic compactifications. So let me plot these things. And as I said, these are just previews. So I will finish by having all this picture completed. So there are actually two nicer kinds of things in terms of algebraic geometry. So this is something people usually call the maybe Satake-Bailey-Borel compactification. This one, in some sense, detects all the modular forms of parallel weights. I mean, they detect enough modular forms. And I think this is a source of all the algebraicity of the things we talk about. So this is a normal projective variety. And in fact, historically, this is the very first place we ever see a variety somewhere in this game. So it is only because of this that we know Shimura varieties are actually varieties. Because so far, they are just quotients of some analytic space. They are just manifolds. But once you actually can embed it into something like this, which is a variety, you actually know the Shimura varieties are open subspaces of this variety. So this is where we know Shimura varieties are real varieties. So Shimura varieties are real varieties. They are quasi-projective varieties. On the other hand, this is actually quite complicated in general because of the singularities. So in some sense, we squeeze too much things, I mean too many things into small corners, and the boundary actually usually have very large dimensions. You are collapsing too many things into small points. So there are some nicer ways to sort of make this geometry simpler at the expense of putting in some combinatorial data. So there is something we call toroidal compactifications, which are nicer in this sense. But this depends on some choice. I will actually, well, maybe I won't have time to say very much about this, but anyway, there's something nicer. This one can be smooth and projective for good sigma. But the price you pay is that this is not canonical. You have to make some choices. On the other hand, this is really just nice things. The boundary will become divisors. You can actually explicitly label all the components of that, and you can study them rather explicitly using those data. Unfortunately, these two things don't seem to be compatible. They are quite different from each other. In some sense, the topological structures look very much like dual of each other. So the ways that the things cross each other here are different from things over there in the kind of dual way. And also, the Borel-Serre compactification is different in another sense. So this Bailey-Borel compactification only requires the so-called, well, I will repeat this next time. So they only require the so-called maximal rational parabolic subgroups. This one actually uses all parabolic subgroups, not all rational parabolic subgroups, not just maximal ones. This one only uses maximal ones. So in some sense, these two algebraic things are similar to each other in this sense. And that one is basically just retains almost every information you want for studying automorphic forms in cohomology. Anyway, I think you will see some applications this afternoon. in previous lecture. Okay, I will stop here today.